Let's look at applications of the Sturm-Liouville theory that we have built. So the first application is the review of the example that we have been carrying on through the explanations. So we have the Sturm-Liouville problem, y second plus lambda y equal to 0. We have zero boundary condition on the interval 0, L. Then we can define our self-adjoint operator as hy equals minus y second. Our weight is equal to 1, and we can find the eigenpairs lambda n and yn, where lambda n is n squared pi squared divided by L squared, and yn is sine of np divided by L times x. Both of them, you see, depend on n. So it's easy to see that they're all different and they can be counted. We would like to normalize yn, so we would like to multiply it with a kn to define orthonormal base like phi n. And we want to choose kn such that phi n times phi n inner product is equal to 1. So we check the inner product out, and we notice that in order to have that, we have to have kn equal to n, 1 for all n. So phi n equal to sine of n pi divided by L times x is an orthonormal basis for all continuous functions Vx that are defined from 0 to L and have zero boundary condition on both sides. That means that any function Vx can be written as an infinite sum of Cn times phi n, where phi n is the sine. This is called the sine Fourier series, sometimes just Fourier series if you know which one you're referring to. There exists a cosine Fourier series and there exists a mixed Fourier series. But for the moment, we're just going to concentrate on the sine Fourier series. Not only we know that we can write Vx as an infinite sum, we also know the coefficients. And the coefficients are the inner product of Vx times the eigenfunction we're looking at. So it's the integral from 0 to L of Vx times sine of np divided by L times x, all dx. Let's look at a second example. In this case, we are really going to be doing a full example of a Sturm-Liouville problem. We're looking at the same ODE as before. Y second plus lambda y is equal to 0. This time we're going to look at the interval 0 to 1, and we're going to impose boundary condition, the first one being y0 minus 2y prime 0 equal to 0, and the second being y1 equal to 0. So we have trivial boundary conditional at 1, but something that is called a mixed boundary condition at 0. Mixed because it involves both y and y prime. Is it a Sturm-Liouville problem? Well, px is equal to 1, wx is equal to 1, qx is equal to 0, so as far as this goes, we're okay. And alpha is equal to 1, beta is equal to minus 2, one of the two is not 0, gamma is equal to 1, delta is equal to 0, so not both of them are equal to 0. We can also check that the determinant of alpha, beta, gamma, delta is different than 0. But I haven't been looking into that, so let's not look at that. So it is a Sturm-Liouville problem. Now we want to find yx that satisfies our Sturm-Liouville problem. If lambda is equal to 0, well, y second is equal to 0, yx is a first order polynomial. We have to satisfy the boundary conditions. So if we satisfy the boundary conditions, we have that a is equal to b is equal to 0, so we only have the trivial solution. Not that exciting. Let's look at lambda different than 0. Then we can use this characteristic equation to find out that y needs to be the sum of sine square root of lambda x plus cosine of square root of lambda x. We can compute the first derivative, and then we can apply the boundary conditions. So we have d minus 2 square root of lambda c is equal to 0, and c sine of square root of lambda plus d cosine of square root of lambda also equal to 0. This is equivalent to a 2 by 2 matrix system. This is a matrix system that is equal to 0. This has a non-trivial solution only if our matrix is singular, only if the matrix that we are looking at has a determinant equal to 0. This is the only way in which we can build a non-trivial solution. So we have to require that sine square root of lambda plus 2 lambda cosine of square root of lambda is equal to 0. Or more compact, 2 square root of lambda equal to minus the tangent of square root of lambda. This is not a closed form, not as we had before, but this is the best we can do. And we have infinitely many solutions that start strictly bigger than 0 and keep growing. We have some approximations like lambda 1 is roughly 3/2, lambda 2 is 23 point something, lambda 3 is 63 point something, and so forth. So they grow fairly fast as well. So in the process of looking for yx, we determined all lambda n such that y is non-trivial. Once we have lambda n determined, we can find yx, because it satisfies the equation we have written before. D we can write as a function of c, is 2 square root lambda c. So yx is equal to c times a combo of sine and cosine. So c is the scaling. We can choose c to be any value, and y would be an eigenfunction. But we want to choose c such that the inner product of y times itself is equal to 1. So let's look at what we can do. Well, let's apply the inner product of y times itself is the integral from 0 to 1 of c squared y times y. Our weight is equal to 1, so we don't care. So here we have sine of square root of lambda x all of power 2 plus 4 square root of lambda sine square root of lambda x cosine square root of lambda x plus cosine of square root of lambda x all time at the power 2. We know that the sine squared plus the cosine squared is equal to 1, so that part simplifies away, and one part stays there. So we want to compute this integral. I'll call it I, is the integral between 0 and 1 of sine square root of lambda x times cosine square root of lambda x. I do a change of variables from square root of lambda x to t. So dt is square root of lambda dx. So we can simplify our equation to be 1 over square root of lambda, 0 integral from 0 to square root of lambda of sine t cosine t dt. This is the integral of cos squared, so we can compute cos squared. So we have that that our c, our scaling, is equal to plus or minus square root of 1 over 1 plus 4 square root of lambda, where I is also something that depends on lambda. We can choose between a positive and a negative scaling. That doesn't really matter. C depends on lambda, and that's completely fine. So we have found c lambda n. We have found phi n with the c scaling just defined, and we know that phi n is a orthonormal basis for all functions on 0, 1 that are continuous and are satisfying the boundary conditions.